Alright, let's jump in. Today's class recording has started. So, in all honesty, if you want to receive notifications when I post things, you can subscribe to the channel, because really I do have a YouTube channel. And you can ding the bell.
You get any revenue?
What?
You get any revenue from this?
No, not that I'm aware of.
Not sure.
Alright, so over the past couple days,
What's your YouTube channel?
I think it's Mr. Planasec WHS. So,
Oh, I found it. Look at subscribe.
so I think it is Mr. Planasec. My old YouTube channel used to be Planasec WHS, but then when we got new school email addresses, I had a YouTube channel. So yeah, but yeah, Mr. Planasec WHS. I think it is. So. Say again. No. All right. So over the past couple days, we have been building this complex drawing. What is this a drawing of? Let's make sure we have that down first. This is a drawing of orbitals, okay? What are orbitals? Previous electron location, which we then use to say what? We predict where they might be in the future. If they've been there in the past, that's where they're going to be in the future. So, we talked about that there are two sort of factors if we look at the pattern that we developed over our course of making this drawing. There are two things that we've looked at, right? What happened as we got farther and farther and farther from the nucleus? What changed? Energy. Increase of energy, right? And how did we sort of signify that in this drawing? What did we use? The colors, right? Every time there was a color change, that sort of signifies a significant increase in energy, okay? But then, the other thing, the other pattern that sort of developed, is what? What else did we sort of see repeating as we went along? First shape was a sphere, then the next shape was hourglass, and the third shape was butterfly or the dragonfly or whatever, okay? So, Mrs. Dunn. All right. So there is a pattern that develops here as far as the energy that's involved and then the shape of the orbitals as we move along. We said that this happens because there are two basically competing factors that determine where these orbitals set themselves up. What are the two competing factors that sort of determine this?
They want to be closer to the nucleus and farther away from each other.
Electrons are trying to be close as they can to the nucleus while trying to stay far away from each other as they can, right? So we have those sort of competing factors, okay? All right, that being said, we went here, and on Monday we introduced the idea of quantum numbers, right? That each orbital gets assigned a set of numbers, and those numbers distinguish that orbital from all the other orbitals on that picture. There are 4 quantum numbers that we use to distinguish that orbital. And so each orbital has a unique set of 4 numbers that makes it different from all the rest of them. Yesterday we introduced the first quantum number, and we call that the principal quantum number. In sort of a shorthand version, what does the principal quantum number describe for us about that orbital? Do you remember? Energy. Okay? In a big, broad sense, all right? Orbitals that have lower principal quantum numbers have lower energy electrons. Orbitals that have higher principal quantum numbers have higher energy electrons. Good?
What was you?
Thanks. I decided not to sneeze into the microphone.
That was really funny, man.
All right. Good there? So we said, pattern-wise, there's 2 things we look at. Energy, and then shape. So principal quantum number, which we use as big lowercase letter n, represents the energy, so now we have to talk about the shape. So we get into that when we talk about energy sublevels, okay? So within each principal energy level, we say that there are sublevels. Okay? And the first sublevel in each principal energy level, PEL, is labeled as S. What was the first shape that we drew in every single color that we started out, or that we sphere, right? The spherical orbital is the first sublevel in each principal energy level. And we refer to those spherical orbitals as S orbitals. Okay? Do we have this written down here? Let's finish writing this and then we'll go back to our picture. Okay? Okay, good? All right. If we go back to our picture, okay, this is the first orbital that we drew. It is spherical. We'll get to that in a second here. All right. This is the first orbital that we drew. It's spherical, and so it's an S orbital. This is the 1s orbital. Okay? This is the second orbital that we drew. Right? It is also spherical, but its energy changed. Okay? So we went up an energy level. So this is also an S orbital, but this is a 2s orbital. Okay? Sorry, I should maybe break that. Okay. Right? So we would call this orbital, now I won't write it in yellow because that won't show up very well. Okay? But this orbital we call 1s. And then this orbital we would call 2s. Okay? And you guess what we call this one? This is 3s. Okay? They're all spherical. Okay? But they go up by energy level. Okay? This is where it might be helpful to maybe use the smaller ones down at the bottom, but if you can keep them straight, that's fine. Totally up to you. Okay? All right. Good with that for starters. Okay?
Well, is this just like the orbital blocks and colors and everything?
Yeah, how do you, Jack, I don't care where you write these things as long as you understand what they mean. Okay? So, the next shape that we drew was our hourglass. Okay? Now notice, there's no yellow hourglasses, right? Yellow only had a sphere and nothing else. Okay? Hourglasses don't show up until we get to the red level, so the second level. Okay? So the fact that this is a 2s orbital and this one is the same color, this is still going to be a 2 orbital. Okay? But it's a different shape, and so we have to distinguish this shape from the previous shape. Hourglasses we call p orbitals. So this orbital here would be a 2p orbital. Okay? Hourglass-shaped orbitals are called p orbitals, so this is a 2p orbital. But the next one that we drew looked like this. First, what color is it? Red. So that means we're still in the 2 level, right? But what shape is it? Hourglass. And we said that hourglass orbitals we call p orbitals. So this one is also 2p.
Wait, so can you just, so if you're saying that, can you just make like the 2 crossings?
So that means that if the one on the x-axis is called a 2p orbital, and the one on the y-axis is called a 2p orbital, the one on the z-axis also is going to be a 2p orbital as well. So now we have 3 different orbitals, but we've labeled them all the same way. So somewhere, somehow, we're going to have to come up with a way to distinguish the x-axis from the y-axis from the z-axis. We're not there yet. Okay? Right now we're just focusing on color and shape. What energy level is it in? What shape is it in? Okay? Good there? So we said this one is an s orbital because it's a sphere. But it's a different color, so we made it a 3s orbital. Okay? What do you think we're going to call this one? 3p, right? It's still an hourglass shape, but now we've taken it up another level. Take a wild guess. How many 3p orbitals are there going to be? 3 of them. Okay? X, Y, and Z. Okay? But once we got past those, we added in dragonfly. Right? Okay? Remember what we said, that this whole thing, right, this is all connected. This is one orbital. It's not 4 separate places, it's all one orbital. Okay? Dragonfly orbitals are called d orbitals. That was totally a coincidence, because I don't usually use dragonfly to describe the shape of this orbital, but you guys decided on that yesterday, and I was like, cool, and so now d dragonfly, there we go. Okay? I might, yes. Although the afternoon class didn't like dragonfly. They went with pinwheel. Okay? So, like a pinwheel? Yeah. Alright. So. But what level is this dragonfly orbital in? It's in the 3rd level. So this dragonfly orbital would be a 3d orbital.
Oh my god.
Okay? Alright, are we okay with the pattern here? Okay, kind of see how it goes? Alright, so the quantum numbers, oh, sorry, one last thing before we go back to the quantum numbers. I told you yesterday, do we remember how many d orbitals there are? It's actually 5, okay? So I didn't make a big deal about that yesterday, but there are actually 5 d orbitals. So we said one's between the x and the y-axis, one between x and z, one between y and z, but then there's 2 other ones that are kind of crazy, so we won't get into that too much. They're kind of like, one's sort of like an hourglass with a donut around it, like around the middle, so it's not really like, yeah, it doesn't sort of fit the pattern, it's kind of random, that's why it's hard to like describe all of them, because there isn't a distinguishable pattern. Like p orbitals are always hourglass shaped. S orbitals are always spherical shaped. But d orbitals sometimes are dragonflies, but sometimes they look a little different. So it's not quite a distinguishable pattern. Yes, Ken? Oh, in this case, if you draw one d orbital, I'd be perfectly fine with that. So yeah, like that. Just knowing that that other shape exists, Kendall, will be fine. But actually, when we get into the notes, you'll see that there's actually a 4th shape called an F orbital, but we can't draw that. It's too complex. So, okay. All right. Good so far.
Could we look at pictures online?
Yeah, I actually have a picture. There's actually a picture in your outline that I'll show you in a little bit. Actually, if you go to the F orbitals, there's a chart at the bottom of page 2. For F orbital, it just says 7 complex shapes because it's just it's too hard to draw. So you definitely need 3 dimensions to do that. Okay, yeah. All S orbitals are spherical. All right. So that was another d orbital, okay? But then we added this next s orbital, right? No. This. So which orbital would this be then? Which orbital would this one be? For what? 4s, because it's a sphere and it's in the fourth level. Okay? All right. Okay. So, the principal quantum number tells us the general energy level or the energy of the electrons within that orbital. Okay? The next quantum number that we come across, and if we go down, I think this actually gets to the next page, is... Yeah, we'll come back to that in just a second. Okay? So, go to page 2. Okay? Roman numeral 5, the angular momentum quantum number. Okay? We use a lowercase l to represent the angular momentum quantum number. So a lot of times I'll draw it kind of cursive so you can tell the difference between L and I or 1 or, okay? So if you go to page 2, Roman numeral 5, okay, we use the lowercase l to represent the angular momentum quantum number. The angular momentum quantum number tells us the shape of the orbital. Any s orbital, regardless of what color it is, any s orbital is a sphere, and we say that it has an angular momentum quantum number, an L value equal to 0. Any p orbitals, any hourglass-shaped orbitals, have an angular momentum quantum number equal to 1. So L will equal 1 for p orbitals. Any d orbitals, which we kind of use as our dragonflies, have an angular momentum quantum number equal to 2. And then f orbitals, we get to 3. So, if we go back to our drawing, let's go right here. Okay, oh, no, let's go to this one. Okay. We called this a 1s orbital, but we said that there is a set of quantum numbers that describes that orbital and makes it different from all of the other ones. Okay? So the first angular momentum, or the first quantum number that we talked about was n. N for this orbital is going to be equal to 1 because that's the lowest energy level, the closest we can be to the nucleus. Okay? The next quantum number that we introduced, we called L, lowercase l. N tells us the energy, L tells us the shape. S orbitals are all spherical. What value do we assign to spherical orbitals for the L value? You remember from we just had it on the previous page? 0. Okay? So for this orbital, n equals 1 and L equals 0. Okay? Good with that so far? All right. For this orbital that we call the 2s orbital, n is equal to 2 because we moved up a level, right? But what is the shape of this orbital? It's still what? It's still spherical, right? This one's still spherical, right? It's a hollow sphere, but it's spherical, right? Okay. All spherical orbitals get an L value equal to 0. Okay? Good so far? So now, for this one, we already have a different set of quantum numbers than we do for this one. Right? We've already distinguished the yellow sphere from the red sphere with these 2 numbers already. Good? Okay? I'm going to go here, right, and show you all 3 of these together, okay? We said that all 3 of these hourglass orbitals are all in the second energy level, so they're all 2, and they're all hourglass shaped, and any hourglass shaped orbital is p. So these 3 orbitals are all 2p orbitals. Okay? Good? Yes, no, maybe. Okay. If we're coming up with numbers to represent these orbitals, right? Remember an address for all these orbitals, okay? N for this one is going to be equal to 2 because it's still in the red level, so N is equal to 2 for the red level, right? And then L, which tells us the shape of that orbital, okay? If you look back on page 2 of your outline, what number do we assign for L for hourglass-shaped orbitals? 1, okay? So for this orbital, this x-axis one, right? If we look back on the previous orbital that we just named, oh, not that one, this one, N was equal to 2 and L was equal to 0. For this one, N is equal to 2 and L is equal to 1. So they're different. Good. But if we start looking at these other orbitals, the y-axis and the z-axis, this one still has N equal to 2. And because this is a p orbital, right, an hourglass-shaped orbital, L is equal to 1, because all hourglass orbitals get an L value equal to 1. Yes? You okay with that? Go ahead. The P describes the shape of the orbital. So all P orbitals are hourglass shaped. Okay? So these are 2p orbitals because they're hourglass-shaped orbitals in the second energy level, right? But then we said that, like this one, so this one here, this is also a p orbital, but it's in the third energy level, so it's still p, but this is 3p, okay? Are there any 1p orbitals? Were there any yellow hourglasses? Nope, right? There's only a 1s orbital, okay? P orbitals don't start until we get to the second energy level. Kendall, go ahead.
For the red,
Yep.
we have to write down the ones too.
Technically, they're there, okay?
So, like, would they be
So, Kendall, let's go. Let's do 3D first, okay? Okay. Actually, well, here, let's go start here, okay? So this one, 3s orbital, right? If we start identifying quantum numbers or assigning quantum numbers to this orbital, here, N jumps up to 3 because we've gone from red to blue. Okay? But the L value talks about shape. Even though this is a bigger one and it's blue, it's still what shape? It's a sphere. What do we assign as the L value for all spherical orbitals? 0. So this one is N equals 3, L equals 0. This one is N equals 2, L equals 0. And this one is N equals 1, L equals 0. Okay? Followed me so far? Blue hourglass. Because it's blue, N is equal to 3, right? But because it's an hourglass, what value do we assign to hourglass or p orbitals? 1. Okay? But that's true of this one, and this one, and this one, because they're all p orbitals in the third level. Okay? Here's 3D. Because it's blue, and because it's in the third level, N equals 3. But then, what value do we assign to dragonfly orbitals for L? 2. So this is N equals 3, L equals 2. Following me so far? Good? Okay. So, let's fill out the part of the outline that we skipped, and we'll go from there. Okay? So we talked about that the first sublevel in each PEL, principal energy level, is called the S sublevel. We know that S sublevels have which shapes? S orbitals are all what? Spherical. Okay? There's 1s, there's 2s, there's 3s. Okay? I don't think you guys have this picture, but okay. Let's finish this up and then we'll be done for the day. Okay. All right. The second level, we call it the P sublevel. P sublevel orbitals all have which shape?
Hourglass.
All P orbitals are hourglass shaped. Okay? But, like I said, P doesn't start until we get to the second level. Okay? How many P orbitals are there in each level? How many hourglasses are there in each level? 3 hourglasses. Right? 1, 2, 3. Okay. All right. We'll continue on this on Monday, and then we'll start talking about how we make this shorthand. All right? Because this can be a little, it's a little overwhelming. Okay?